So when I stopped, so this is the approach in terms of GINA science, but as an astronomer, I do use opposite way. So because we understand some of the formation and evolution history of this element, we can use that information to understand what happened in the back in the past. So that's what I'm going to talk about it. And I'm not going to go deeper, and I'm going to give you an overview and big picture of what we do. Then I think I have to go this way. Okay, this outline of talk will be about half an hour Galactic archaeology lecture. And then I'm going to share with some of my graduate experience and how I become this far. And maybe you can relate some of the story. And then I'm going to show that what is the astronomer's day-to-day life. And then finally, I give you some information about the graduate study at Notre Dame. And then I want to start with this questions. When you hear about the word archaeology, what kind of thinking comes into your mind? So usually if this is in-person class, I would ask individually, but it's a Zoom, so I'll start with mine. So when I hear the archaeology, this poster is thing that I can think of. I don't know how many of you know of this series. This is a movie series called Indiana Jones. I think here are many old folks, so you know that what they are. So this was my first encounter with that. I'm sorry? Oh. Okay, it's fine. So this is my first encounter with the the archaeology itself. So this is the guy who is an archaeologist to try to find a treasure. And there's so much interesting story in there. And then second image is this King Tut, King Tutankhamun, right? I don't know how many of you know this guy, but I was fascinated by the story of this discovery of his tomb. The King Tut is not particularly important person, but his tomb was a very important discovery in terms of Egyptology. So the Dr. Carter, who was an archaeologist who really discovered this tomb, they knew some of the information about where this tomb was hidden, but it was a vast area. So the way they approached it to find this one was very systematic. You cannot randomly go and pick in and find it, right? So they did section by section, which means it takes a lot of time and a lot of collaboration. So he can't do it alone. So he worked with so many people at the museum or excavation people. It was a big, huge collaboration. And then not only that, they have a limited time to find this treasure. So time was ticking and they couldn't find it. But then by the time that really close to the deadline, they were indeed find this treasure. This like tomb was hidden somewhere. So it was a great discovery because this tomb really preserved most everything except some few robbery. So we can understand what happened during that era, and especially this king's era, king's life. So that way we study this archaeology, right? And then some of you may think all the historical sites and some fossils and some digging, and sometimes you get some really treasure from this hunt. So then how we do as a Galactic archaeologist study universe, right? I mean, this is the terrestrial archaeology. We study this human history, right? Through all the stuff. So how we do that, how do we learn about this history universe? And before we go, I want to briefly show you the evolution of the universe, a very brief schematic view. So we know that universe was started with the Big Bang, right? It was very hot and dense state. And as the universe quickly expands, the temperature goes down. And then by doing so, we can create, the universe can create the hydrogen, helium, a little bit of lithium. Out of that, the first star was born. And then afterwards, there are so many diverse astronomical bodies was formed out of that. And then now we have about 14 billion after the Big Bang. We want to study this particular era. Especially as a galactic archaeologist, I'm very interested in first stars. They are very important, not only because they're first born, because they capture very important physical environment condition at the early universe. The formation of first stars are quite different than current day star formation. Only reason is that, as I said, in the beginning of the universe was much hotter than current day star forming environment. Because when you have a gas, if it's really energetic, you cannot really condense easily. So the way you can condense is you have to have a lot of material to collapse. So the first stars are very massive, and you will learn more about how stars are going probably next lecture by Artemis. But basically, they use this hydrogen, infuse them into the helium. The way they grow, they live that way. But then these are very hot and dense state. They really use the hydrogen quickly, and they really quickly. So even though they formed really early on, they're disappeared. But then the next generation stars, they're formed out of this clouds with mixed with these first star remnants. So we are trying to find those treasure stars. So then the traditional way to study the old or early universe is a look back in time, right? So this diagram shows as a human endeavor to try to probe the early universe using this various telescope. As time goes, you see the technology advanced, our ability to back in time is really enhanced. So now we have James Webb Space Telescope launched. They're gonna, it's gonna observe many things. In particular, they promise to give us very beautiful pictures of first galaxy. But the problem with this is that when you look at this left-hand side diagram, I mean the picture, you see this is the 1 degree square of imagery in the sky, the moon to the scale here. And this is relatively a lot of star, but you cannot really see any galaxy there, right? But you see the little patch of sky here. This is actually Hubble Extreme Deep Field and looks like a very blank sky. But people want to know that is there something there. So what they did is put a proposal to observe this small patch of sky for a long time. It's about 500 hours. That's a pretty long time for the even ground-based telescope, but this was used as a space telescope. So what you find is the right-hand side. There's so many galaxy clusters and galaxies. You see a lot of stuff. So you can learn some of the overall structure, overall behavior, but the problem is that you can't really resolve any single star there because it's too far away. And then with this 500 hours exposure time, you can't really have many as possible. So we need to have a different way to study this early universe that comes in with this galactic archaeology. So simply as Earth, the terrestrial archaeology, we study this early universe history through the stellar fossil, and they are still living our own galaxy. So you don't have to go really far. You can just observe these stars in our own backyard, and then you can know a lot of details that the far field study cannot give us. So before you go, this is a quick question. So maybe Anna, can you make as a poll? Yeah, this is a question you can answer to. It's okay to be wrong, and if you are not an astronomer, you don't really think about the age of the universe. But if you pay attention to my talk, the previous one, you can get some idea. So can you?
You can vote now.
Yeah, this is easy. It's okay to be wrong, so just do it simply. So feel free to just push a number. No one knows that who answered what. So we just want to just make you engaged and focus on the talk.
All right.
Do you have a result?
We have 45% of the people have voted. So you have a couple more seconds. Come on, don't be shy.
Yeah, don't be shy. This is not really, yeah, just guess, it's okay. I mean, I can tell you before I start working as a galactic archaeologist, I didn't really think about what the age of universe. So totally fine.
Okay, I'm gonna close it now.
Mm-hmm. Do you have a result? Oh yeah, most of them you're right. I think some of them might be confused with the million and billion. Yeah, that was a tricky part, but yeah. Okay, great. So the answer is, answer is, see, Yeah, answer is 13.8 billion. So it's about 14 billion years old, that old. So next question is when do you think it first star was formed? When the universe was how old? Can you put up another poll? This is a very difficult question. Even Anna didn't know that, right? So unless you study particularly this first stars, you don't really know when they're born actually. So it's okay. Just I want to give you some idea and guesswork and don't be shy. Do you have results or not?
Okay, last 5 seconds. Okay, here are the results.
Yeah, okay. I'll show you the answer. Answer is, okay. Oh, sorry. Answer is 3 million years old. Yeah, this is pretty young age compared to the age of the universe. So when you look back this diagram, you see actually the first star is born about 400 million. This, there's a precision issue, so you don't have to worry about the number itself. It's about, this is the few million years old scale compared to age of universe is 14 billion. So the age is pretty old compared to our human life, but they compared to universe life, it's very short. So these first stars are born right after the Big Bang, and then they die quickly after that. So next to, so we are here and trying to understand this part. And so before going into, more detailed galaxy archaeology, I want you to think about what you can guess from this, this comparison between archaeology and galaxy archaeology. I would ask you questions in person, but this is Zoom, so I'll just show you some comparison. We can think about the similarity, right? Because we study all the stuff, right? So in archaeology, if you look at the sky, you try to find this old stars and stellar fossils, and as the archaeologists need some special tool to find these fossils, we also need special tool, which is telescopes, right? And then they do a lot of digging, and we do a lot of digging, data digging and analyzing. But then difference is here because one is can be done in the earth and the other is in the sky. So difference is that we cannot visit star. We cannot go to sites, and we cannot touch stars and galaxy. Unlike the archaeology, we don't have many observable. We just only have light. But light has lots of information we can learn from it. So we try to use this light information to really decode what happened early on. And then there's no direct record from the star, right? I mean, yeah, the archaeology stuff, they even hold, people in the past, they left some direct records. So that's different. So based on this comparison, you would guess what we do. So to understand the galaxy archaeologies, you just need a 4 different step concept. One is, the how the star evolved, and then because of how our universe enriched with chemical elements as a function of time, and then because we only have light, we need to be able to understand what the nature of light, and then using that we get the information. So to analyze light, we need to have special tool called spectroscopy. I'm going to talk about a little bit about that. And then there's a way that study this old object, and by looking at their stellar motion, we use a kinematical analysis, but we don't have enough time to go that. So I'm going to just focus on spectroscopy. And then we have observable and a method. But then what we do is that we need to find these stars. And then I'm going to talk about how to find these ancient stars. And then from that, I can talk about a little bit about the first stars. So then you can ask question that, this is the nuclear astrophysics lecture. How and why are astrophysics and nuclear physics connected, right? One studies is super big, astronomically big and far away, so we have to use a special telescope to observe. And the other one is so tiny that we cannot even look at with a microscope, right? So we built a special tool such as accelerator to understand what happened in the really, really small scale, nanoscale objects. So how they connected. That actually comes down to these two physical parameters, temperature and density. I'll let you know what this means here. So this is a very simple schematic graph I'll show you. This is the temperature of universe and density of universe as function of time. And we need to know that this Big Bang happened, right? When Big Bang happened, it was a hot and dense state. And as the universe expands quickly, and the temperature cools down, right? So then the cool enough that the hydrogen, helium, and a little bit of lithium can form out of this Big Bang. And then more colder, and then this gas contracts and becomes star. And then because of the contraction, and that makes the core of this pre-star, protostar or star becomes hot enough that this hydrogen fuses into helium. And then depending on the mass of the star, if the more the mass, you have much higher gravity and makes it hotter inside, so that you can even fuse helium to carbon or oxygen and up to iron in the star. Then by the time they make all the iron, there's no more fuel to fuse these elements, because iron is the most bound state. You cannot make a more bound state than the iron. So basically everything collapses. Because of collapse, the sudden collapse, there's a shock wave happens outward the star. So then this shock wave ejects the elements, and this is we call like supernovae. And this supernova event is very hot and dense enough that you can make more elements, heavier elements than iron. And then this element created inside the star actually ejected through this event, and then later cool back again, right? Then this element mixes with the cool hydrogen helium gas, and then from there, the next generation stars form again. So this is a really cyclic event, and multiple generations star formation happen throughout the time. So by the time now, we have a lot more elements than the beginning of the universe. This is where the nuclear physics, astrophysics meet. So we have such a different object, different like scale, but astrophysical environment to provide the environment that these little elements can form. This is the nuclear physics. So I told you that depending on the mass, this is really busy diagram, but you don't need to hang up with the too busyness here. What I want to show you is there, depending on the mass of the star, they have a different phase. And because they're different phase, different mass, and they have a different physical condition to create such a special elements, and then amount of those elements. So that's what just you need to know. So based on the element that we find from stars, we can trace back what kind of physical environment or their parent star would be. So that's what we do. So important thing is that end of the stage of its stellar evolution, between the low-mass star and massive star, they are making up different elements. So low-mass star, because it's slow, and then the temperature is hot enough to fuse higher than oxygen. So they usually have a carbon and oxygen core. And then the massive star is much hotter and dense state. So you can make up to iron here. So important thing is you see the core is really small compared to the size of the whole like star though. And then one thing you need to remember is that this massive star has onion-like structure. So the lighter the elements and the further away from the core. So you have an iron core inside, the outer layer will have hydrogen. So most important takeaway from this lecture so far is that massive stars are short-lived because they use these fuel really quickly. But then low-mass stars are very long-lived because the hydrogen fusion process itself very inefficient. It takes so long. So most of the stars actually spend time burning this hydrogen, and at the end of their lives, they very, very short period of time. And then each stage of stellar evolution and astrophysical events like supernova provide the specific physical environment, which is specific elements can form. So the heavier the mass and more massive, explosive events are the sites where the more heavier elements can form. So based on this simple stellar evolution theory, you can now guess that. So we have a Big Bang here. We only have Big Bang nucleosynthesis elements of helium, hydrogen, and a little bit of lithium. From there, this first star was born, right? But then because they're massive, they're used really quickly. The reason why that's important, because the mass of these first stars are very important. Depending on the mass, you may have a different elements production. So over time, you will have a totally different makeup of a universe. So even you may not even exist depending on the mass of first star. So that's why these are very important. And then they die quickly and they eject the elements and the second generation stars form. By the time the second generation star form, the universe is cool enough and the cloud is very cool enough to make a very small massive star. And as I said, low mass star can live long. So they are still living in our galaxy. That's what we try to find it. One important thing is that in astronomy, we call metals beyond helium elements. I'll tell you later why. So this is another quiz. Yeah, so can you make a poll for this? Anna?
Just a sec.
Yes. So you look at this slide and then think about what star cannot contribute to this chemical evolution, chemical enrichment of our history. Look at this massive 60 solar mass star. They live 3 million. And then the 0.1 solar mass star lives like trillion. So you can guess what, right? Because if you know the age of the universe, remember, what was it? Just guess anything.
This is a tough question.
Oh, it's a tough question. Okay. So the important thing is that the massive lives are short-lived, and then low mass star live long-lived. Then if you want to contribute something, what happened, right? You contribute something through supernovae, right? So.
Okay, yeah. Ending.
You have a question? Right. So they did not contribute, right? So here is the answer, the 0.1 solar mass. Because they're too long lived, they are still young. They can't really contribute anything to the universe. But this is 60 solar mass, lived 3 million years. Then if that first star was born like 300 million years old of age of universe, and they just live 3 million. So basically they explode everything they created, and then they enrich the universe with the mass, right? So the lower the mass, especially this one solar mass is our sun. So even our sun doesn't really contribute to anything yet because they're born about, I think 8 billion years ago. No, I think 4.5 billion years ago. They still need to live another 5 billion years. So they even sun doesn't really contribute to any chemical evolution. So great. Next, so then you know the stellar evolution, and you knew the chemical evolution. So chemical evolution, simply, you don't have nothing. You have nothing in the beginning. Then as over time, because of this, during stellar evolution, you enrich the elements in the universe, and then the matter content becomes increased as a function of time. So, so then now you want to know, if you find this important object, you want to know what kind of chemical composition they have, because by doing so, you can understand their birth environment, and then that the chemical information gives us the first star's nucleosynthesis. So then you need to just know that what is the spectra, stellar spectra, and to analyze the spectra, we need to understand what is the spectroscopy. That's very simple. Stellar spectra gives a lot of information, but we will focus on just the chemical composition. And spectroscopy is a simple way that it's a technique of the splitting light into the constituent wavelength, like prism disperse the light to rainbow colors. Same thing. So I'm going to give you a brief one. If you watch the video in Ascent, you see this solar spectrum. And the video said that this black stripe represents some particular elements inside the sun. And the thickness of this dark stripe actually tells us the amount of that elements exist in the sun. So a simple way to think about it, this is if you have some high school physics, or even quantum mechanics, we know that each element has some special configuration inside the atom, right? So depending on the elements, you have different electrons, and each electron can move around between the different energy level, right? You can't go continuously. You only can leap between the specific energy level. So the way that electron can move around the different energies level is the absorbing photon of some specific energy difference between two level, right? And then that makes us absorption spectrum. And then when you excite it to different energy level, then because it's not the stable, they want to emit that same photon, right? That gives us emission spectrum. So when you look at this diagram here, you have a hot black body. You can think of just an incandescent light. It's a very hot state, and then light comes to us. When it comes to us directly with using the prism, you will see this continuous spectrum because this one has a white light. So basically mixture of every wavelength. But then when this light comes through some cooler gas of some element, that hot gas, right, can observe in this particular cooler gas, depending on the elements. So that observed light doesn't come to us. So you show this black line that light didn't come to us. That makes an absorption line. So when I see this comparison between star is that actually this is not to scale, but when you see the star has a small, very core, that hot dense core, like this a hot black body, and the light from this hot core comes to us. They have to go through this cooler atmosphere. We have Earth has an atmosphere, right? And also these stars also have a cooler atmosphere, and that this atmosphere we call the photosphere has many different elements. But depending on the element's energy state, some of the lights observed in that element, so that light doesn't come to us. So it makes this like very interesting absorption spectrum. But then this is beautiful, but this is not really the practical way to analyze. So as an astronomer, what we do is we count the photon number from each wavelength and then plot as a flux function, as a function of the wavelength. This is the spectrum. By the way, please ask questions if you have any questions. So don't hesitate to ask me. And sometimes I have a blind spot that sometimes some language might be some jargon without knowing. So please just stop me and ask questions. So based on the spectroscopy, people studied the universe, right? They studied the sun and other stars and even interstellar medium to become later on stars. And we find out that actually universe has dominantly hydrogen, helium. So hydrogen is about 75%, and then helium is a 23%. Rest of 2% are the metals, we call metal beyond the helium. So that was actually, this finding was came from this person, Cecilia Payne. She was an astronomer, female astronomer, and she was the one who analyzed the solar spectrum. And first, this discovery was shocking because back then Earth composition was so totally different from this sun's, and people wouldn't believe that hydrogen is a dominant element in the sun. So in the beginning, actually this theory was denied, but actually several years later it's accepted, and this was one of the most important discovery in astronomy history, actually. So then how do we find these ancient stars? So now you have know the stellar evolution, how the galaxy or even our universe evolved throughout time, the chemical composition wise, and then you know how to look at the spectrum now. So I'm gonna give you a little quick quiz. Remember that the spectrum I showed you before, I have 4 different spectrum. Which spectra do you think represent the stars? So think about when first star was born, what kind of elements there? So here, yeah. So some of the elements like iron and nickel is indicated here, this line, right? All right. So I think you can close the poll.
Okay, good.
Can I see the results? So which one would be like a spectra of first stars, right? So some people ask many, various one. Actually, answer is, answer is this one, the last one. You see the iron here and nickel, they're metals, right? We expect that only will have hydrogen helium line, not any other elements, because the first star was born out of just a helium and hydrogen. So you can see the first one is actually the sun spectrum, because when sun was born, it's about like 4.5 billion years ago. So there are still a lot of metals. So that's why you have so many lines here. We call them like metal rich star because there are lots of metal. And another way we call like population 1. And there's here 2 stars. Actually, you see that now some of the lines have disappeared and only strong iron and nickel line exist here. And then when you look at this one, it's much more metal-poor than this one. So you see the strength becomes smaller. So these are, we call the old star. These are the Metal-Poor star, and we call population 2 star. And then last one is this is the first stars that this is a hypothetical spectra because no one never ever observed first stars because we think they're all die, right? So hypothetically, you shouldn't have any spectral line here. So anyway, yeah, this is the kind of question that I wanted to share. So you saw that now when you look at the spectrum, if you see the very small line or very weak line, but if supposed to be big, then they're likely to be older stars. So we try to find the middle couple stars. So then how do we find? There are so many stars in the galaxy. You see so many stars, even the Milky Way, the strip. And how do we find it? We cannot observe stars directly, one by one, as like Howard Carter, they can't do everything. So what we do actually use the imaging. So when you see the star and the imaging data, you see the different colors. Actually, remember that when you remember the black body radiation, if you're the higher, the peak of the black body radiation, that gives us a kind of color to us. So the blue color means the blue photon. So these particular stars emit blue photon more than other colors. So that's why we perceive as blue star. So which means blue peak means that's a hotter means the massive, which means massive stars they have a shorter life. So basically they are young star. But then if you see the red star, because they're peak in the red wavelength, which means they are cooler. So cooler means they're smaller and they are older. So this way, simply you find the stars out of imaging first. And then you go with the various level resolution of spectrograph study. So first time you can't follow this start with the high resolution directly because it's too expensive. So the way we do is a really low resolution with the small telescope because this is more reasonable to use it and not expensive. And so when you look at the low resolution spectra, you cannot really resolve many lines, but if there are strong lines, you can still resolve that. And then in particular here, calcium line, when you look at the low resolution, they are very prominent lines. So if you see the more weaker the line, which means there less the calcium exists in the star. That way, pick the candidate, and then we follow with the medium resolution spectrograph. And now you have more resolving power that you can see other lines too. So then you compare it with this observed spectrum with the theoretical spectrum that you would expect of some certain metal content. So then you find it, and then you finally follow with the high resolution. Now you see a lot more lines visible here because you have a higher resolving power. So then now we can do the very detailed abundance analysis. So then if we find this Metal-Poor star, then what we learn about from there. So to do so, I think I'm gonna quickly move on this one, but simply we needed some special like term to discuss of stars based on the matter content. Simply, we define the called metallicity, which means it's simply the matter content in a star. But we use iron as indicator because this is a kind of prominent element for the Metal-Poor stars and also one of the most abundant elements. So we compare this stellar metal contribution compared to hydrogen, which was from the made from the Big Bang. So this is simply the ratio between iron and to hydrogen, but we don't know stellar other stars like content, how much it should have, right? So we compare with the solar spectrum because we really well know sun's abundances. So this bracket sign actually makes the comparison between the star and the sun. So if you have a -2 of metallicity, which means that the star has 100th of metal, so iron, compared to sun. Then I think because we are running out of time, I'm gonna skip some question. So that way, so the lower the number, the metallicity, which means we have less metal and content in the star, right? So if you have a lower the number, that's going to be more pristine star. So when people studied, we found many more Metal-Poor stars, and you see you have a stronger lines here because this star particularly about 10,000th iron content in the star compared to the sun. So which is really a small amount in the star. And then even this star is -5.3 and -7. This is what is it? 10 millionth of the sun's content. So you can see as you see going down that you lose really information. So you don't have really iron elements in here. But interestingly, we see the depression of this the weakness of ion line, right? And then further here, you disappeared. But somehow when you look at this particular line, interestingly, though the metallicity is very low, but you have very strong line here. This is actually CH molecule, so which means this particular star, somehow they don't have iron or other elements, but have higher amount of carbon. So they are carbon-dense Metal-Poor star. And particularly we use this, the relative abundance ratio, carbon to iron. If this bracket number is compared to sun, right? If value is 0.7, think about 1.0 is 10 times more than sun. So it's about, I think, 50%, no, 5 times more than a sun has. So they're very carbon enriched, but then really Metal-Poor. Other elements are very poor. So when you look at the distribution of this Metal-Poor star we found, and we plotted the carbon to iron ratio as a function of metallicity. So if you go down here, that more pristine and less metal there. But then somehow this carbon to iron ratio, it's increasing, really super enhanced. See here. So 5 means, right, 100 1,000 times more than sun has this value. This is a sign that the carbons are the real first elements that ejected from the first star and polluted our universe. So then what we found based on these stars, actually they are called the carbon-enhanced Metal-Poor star with the no, but that's not important. So we think we found the descendants of these first stars. From there, we found out some of the important key aspect. And I'm gonna just briefly share the couple of things. One is that how they produce a lot of carbon. And as I mentioned that the massive stars, the first stars are really massive, and then when they contract because of the conservation of angular momentum, that really rotate fast. So these massive stars are rapidly rotating. And you think about when you have some really rapidly rotating area, everything is mixed inside. So when you think about your washing machine, you put some clothes and the water, and then you push the button and everything is mixes, right? So that happened. Remember the onion structure of massive star? So actually carbon, nitrogen, oxygen is a little bit inner layer than hydrogen, helium. But then because of this mixing, that can be floated up to the layer, the outside of the star. And then there are strong stellar winds happen, then these elements can be ejected from the system. And then the second generation stars actually formed out of this carbon and enriched gas. But then not only carbon, actually nitrogen, oxygen also enriched in the system. And then there is another way to explain this this pattern of these stars is called the faint supernovae. So you know that supernova explode are the exploding stars. So they basically explode everything they created during their stellar lifetime. And then, but then somehow this type of supernova doesn't have high enough explosion energy, but only outer layer can eject it from the system. At the time, this also carbon, oxygen, nitrogen get really ejected out of system, and then this elements mix it with the hydrogen, helium gas nearby, and the second generation star is born. And then this carbon, nitrogen, oxygens are very important in terms of our human life because we are carbon-based being, right? So then I want to ask you one last question. So yeah, this is question. What is the metallicity of the human body? Do you think we are metal-poor or metal-rich, or solar metallicity? So I think you can close. No one knows this answer. I lately knew this answer, so you can just guesswork. So then, okay, I know the answer is, okay. So answer is, actually we are metal-poor, and particularly we are carbon-enhanced metal-poor being. So when you look at the body composition, here we have a lot of carbon, oxygen, nitrogen, and also hydrogen. So when you look at the individual elements information, this is metallicity, this is metal-poor, and then carbon to iron is really enhanced. So we are carbon-enhanced metal beings. So we are so close to first stars. So I'm gonna end my lecture with this chart, and you can see that our body 73% is from massive star, and then low dying mass from the this 70%. So this is my Galactic Archaeology lecture part, and I think I went over, and I think because of the we introduce ourselves. So maybe Hendrik or Anna, do you want me to just quickly go to the career thing, or should I give some opportunity to ask questions?
Well, if there's an immediate question, we could take it now.
Okay.
And then, yeah, a little bit about careers.
Yeah, I think it's time past that. I think right?
We'll
So
run a little bit over. I hope that's okay. But are there any immediate questions right now? And you can.
Yeah, I think I saw some question here. Is the spectrum infrared? I don't know which one you're talking which is spectrum, but what I showed you is more the optical, the visible band. But there are actually telescope that use the infrared too. Yeah.
If you would like, you can raise your hand, for example.
Or you can unmute yourself and ask some questions.
Okay. Okay. If there's nothing urgent, let's hear about careers, and then you can think about your question to score another point for the mark for afterwards.
All right. So then I can go for briefly my academic career history. So I don't know how many of you can relate with me. I didn't decide to go to grad school until my undergrad, and I didn't know anything about grad school. But once I start learning the major physics, it's particularly modern physics, I was fascinated by the concept and the knowledge. So I wanted to study more. But then at the time, I thought only rich people can study further. And I wanted to study in abroad, but I didn't have money to go. So what I did is I went to a local other university for my master's because I didn't know how to come to US. But then that school, my master's school, is already really well established university. So many people actually in our department, physics department, actually they plan and they prepare for the study in US. And then at that time I find out that you can learn free. So you're paid to learn and do cool science. That was very great opportunity for me. So how I did choose astrophysics, and I want to tell you that my undergrad school didn't offer any astronomy courses, and so I didn't have any background, but I just have just interest. And then to study astrophysics, I applied for many schools in US, but many schools actually had both physics and astronomy. So that way I can apply for grad school. So first my try didn't work out. I didn't get any admission. But then I did one more time, and then I was able to choose actually one of the school from the admitted school. So then I could study in US. So basically tuition was waived, and then I have stipend to live as either TA or RA. So first a couple of years I did TA, and then rest of the time I did a RA-ship, so I get paid to learn. And then now I'm working as a postdoc. So you could ask some question, what is like a grad school or academic life? So I prepped some of the pictures here. So basically, any other physicist, we do analyze data, and because I'm an observer, I'm interpreting observed data, and then also, yeah, you disseminate the result through various platforms, and then sometimes you spend time for planning for the observing program. So daily basis, I do look at some archive. Here is the archival database that every day people submit a paper. They're uploaded here, so you can look at the latest paper people are published, so that you keep you updated in the field. And then if you are lucky enough that you have a telescope access, you can go to the telescope site, and then you get some observation too. This was a Keck telescope. I had a really good opportunity to observe with that, but then I had a really bad weather, so I missed that chance. So it was a very sore memory. But then our Notre Dame has access to other telescopes, so I was able to get the data from that observation. So here I show you some of the data analysis picture, and then once you have a good enough results, you can write some paper, the journal paper, and then you submit it. So this is kind of day-to-day basis life. But then occasionally, because you are presenting your work, because you need to disseminate your great result, you go to give posters or sometimes giving talk. There's a good takeaway is that because of that, you have really great chances to travel around the world, and then you meet really great people and international scientists, and you can build a really nice network. And then also these travel are actually usually free, because if you are in a research group, that group has some travel funds, so you don't have to pay out of your pocket. And also sometimes your group doesn't have enough money, but many conferences actually, they provide some support that you can participate in. So there's a many way that you can utilize these resources at grad school if you are interested in coming to grad school. So then I thought, what would you want to know, that why you need to gain something during your PhD or other like academic career. So once you do your PhD, and after PhD, you will gain these various things. Of course, this is also depending on how proactive you are. It's not, you cannot get this free. So basically, if you get a, excuse me, degree, then you have definitely deeper understanding of your subfield, and also you have a big sense of super big accomplishment. And also throughout this many different projects, you will learn how to think critically, and you will build your analytic skills. And sometimes you need a lot of creativity to solve the problem. And also many scientists actually, and especially in astronomy, you will learn a lot of data science skill, which is very important for even non-academic positions. And because of that, you also gain the coding skills, and because of this disseminating events, you will learn how the public speaking skills, and then writing skill by writing your paper. And then if you are in a team or teams group, then you will learn how to collaborate well, and you will learn how to teamwork. And then through that, you will also gain the interpersonal skills. And this is really important, actually. And then also, because you have a various project for making up your thesis, you will have to learn how to manage time and project. And these are very important, I think it's skills that you can get away with your degree. And this is also very much all transferable skills for non-academic job as well. So I think there is a good part of the from the training. And then you would want to know after your graduate what you can do. I think this is as of 2015, that after undergrad, physics undergrad, people got into various sectors. Many of them go to grad school, and various actually department too. And then you can go to military education, other private sectors too. Then after you graduate PhD, what job options do you have? Many people want to go stay in the academia, but not all of them want to go there too. So you can go to university, become a research and professors, or you can go to National Observatory and become an observer and help other scientists to get their observation done. And also you can go to the government lab, and you can become a researcher or civil servant, or even sometimes you become a policymaker. And then these days, astronomy, we have lots of data. So we really need to know how to deal with the data. So you gain a lot of data science skill. So many industry actually looking for people who has data science skill, especially if you have an astrophysics PhD, they really appreciate you. And then some people go to planetarium or science museum, or even some science journalists, or also you can teach at high school. And then, so finally, I'm going to give you some grad school information here. Notre Dame you can see the full information in this website. In our department have all kinds of different branches of physics you can do. Important thing is all admitted students receive full tuition support and the stipend, so you can learn really free. That's really great if you are interested in learning more about science and physics in general. And then deadline is December 15, and this year particularly because of COVID, they decide not to use the GRE scores. Also, the grad school will provide the application fee waiver for minorities that are US citizens. So if you have more questions, you can contact Sherry here. And then I'm going to briefly talk about nuclear physics group and astrophysics group. Nuclear physics group, I think in our department, nuclear physics group has theory and also nuclear astrophysics theory and nuclear structure theories. And then also they have many actually experimentalists. Some people do the measuring the mass of the elements, and some of the people do the calculation for the nuclear reaction, right? So I'm not a nuclear physicist. I cannot really well describe that, but there are many good people. The good thing about the Notre is the lab itself is smaller than MSU, but because it's small enough that as a graduate student, you have a hands-on experience. You can learn how to operate all the instrument. You really are active in that regard. So it's really good for grad school experience, I guess. And then our astrophysics group has all of the kinds of astrophysics happen. So we have observational astrophysics, so stellar galactic astronomy, or if you are interested in exoplanets, you can do the planetary science. And then you also can study the other the elements. You can study some chemical information outside of our own galaxy, as galactic astronomy. And then our school has institutional telescope access. But important thing is that astronomy, you don't particularly need the larger telescope access as long as you have a great science, because in general, astronomy, we have free data, lots of free data. So you can, as long as you have a great idea, you can do really great science. Yeah, and then we also have experimental astrophysics. So a couple of faculty do the optical instrumentation. And then we have a theoretical research that cosmological simulation or simulation of supernovae. So if you want to know more about, you can go to this website, and then you can see this website here. And what else? I think, yeah. And then the one last thing is that ARCHAEO experience. So our university offer this ARCHAEO program. So this is funded by the NSF. So actually, this is a 10-week program. So you get free actually. So as long as you apply, you get selected, and travel and the stipend is covered. So during this 10-week, you can learn the kind of experience that what the research life would be. So yeah, so check it out here. So I think this is all I can say at the moment. So yep. By the way, one thing I want to tell you, if you are interested in more detail about career option, here, these two websites has really great information. So yeah, I want to end.
Okay, thank you.
Yeah.
So who wants to ask the question? You can type in the chat, or you can raise your hand, or you can just unmute and talk. I think we'll pretty informal here. And remember the mug. You can ask anything. Okay, no questions. That's okay. But maybe you can think of a question for next time.
Yeah, I mean, yeah, this is a kind of, oh, yeah, there's a question.
Okay. I was curious that with the changing role of artificial intelligence and machine learning and data science that we've had the past few years, how much has that played a role, or has it played a role yet in some of this analysis, or do you anticipate that to start becoming a bigger role?
So I think my research, I don't use AI, but actually in astronomy, we use a lot of information. So I think the neural network and I think various of neural network, and then there are machine learning that use. So I'm not exactly sure, but we in astronomy, we have lots of data, and then coming another 5 years, we will flood it by that. So sometimes you have a science purpose to analyze data, but sometimes there's so many data, so you don't know what to expect. So I think they try to use this AI technique to get some physical insight. So I don't know at the moment well, but there are people who uses that technology, that algorithm to get some idea or do some great sciences. Yeah. Is that answer to your question? I don't know if that's enough or.
Oh yeah, that was great. Thank you. Yeah, I work in spectroscopy for my PhD, and was working for the past 2 years with Pacific Northwest National Labs in their AI machine learning group. And so I've been trying to apply some of that AI to our spectroscopy research. And I've been finding that that's kind of uncommon at the moment, and others are also trying to figure out how to best apply it.
Yeah, so I think at least, I don't know exactly the neural network is close to this AI, but there's a called Python package, the Canon. So basically you train the data of the spectrum, and then you apply that some like, I think they're called some label, so which is representing like stellar parameter from the spectrum, and then they kind of use that information, apply for the real data. And then I think many people who are in extragalactic study, I think they use some of the deep